Hi, I'm Carl. I work at Foodsby, and I'm going to talk about making illegal state impossible. I've been doing Kotlin since, let's see, 6 months before they announced they were going to Android, so I get to be a total hipster about it. Like, yeah, it's way before it's cool. And so let's talk about what making illegal state impossible really means. The fundamentals of it are that compilation errors are preferable to runtime errors. And you'll see that is sort of you saw in the last presentation that that's sort of a fundamental concept to Kotlin in general. So the first thing to note is that you may already do this. If you're using the type system pretty much at all in Kotlin, you are already making illegal state impossible. So we're going to walk through some examples here, and they're going to get increasingly nuanced or difficult. So how many of you have written code like this? Just takes anything, returns anything, and then is documented to oblivion so you know what to do with that stuff. In general, I would recommend against this. You got some cool nullability checks with that as cast, but you could probably do better by doing something more like this, and just defining your types going in and defining your types going out. You still have to document what that Boolean means, of course, but you get certainty that anybody calling your function is going to receive what they expect. Now, let's imagine that you've built this and it writes to the file system, whatever data important stuff is, and you realize later on, hey, it looks like we're going to be writing to S3 or Google storage. So you take a mode. That mode's a string, and it can be one of several values. You document which values it can be, so nobody screws this up, because if someone screws it up, they'll throw a runtime exception. That's not cool. So the conventional way to do this, and the way I would do this in Java or any language, including Kotlin, is to make an enum class with those values. It constrains them. It's not nullable. Your method goes back to looking like this again. All of the constraints that you have proposed for your code have been pushed to the type system. There is no way to call this trying to upload it to Azure, whatever they have for file storage, right? You literally can't. So as sort of a corollary to making invalid state illegal, there's also making your state more explicit. And I want to talk about this Boolean here and this documentation that output indicates success. So if we look at this implementation of it, you can see the consumption of it. Write some data on the left here is read into a variable called success. It's going to be a Boolean, and you can check it, and the type checker will be happy. But if you imagine that whoever wrote that code just wrote it into some variable called S, anybody going to that code is going to have to go and dig into what your library does, whatever. But if you create a result type, you end up controlling the narrative of how your code is consumed. You get to call it success, and people consuming it have to call it success. The other benefit to this is if your data write result ends up returning any additional information, perhaps you want to return what platform it was on, or you want to return information about a file key where it can be looked up again. You can just slap it on data write result. Anything that doesn't care about that gets to keep working by calling success, and anybody who does care then gains that new information. So this is sort of the basics of it. So we're going to get to the good stuff. Here is something that's a fairly common pattern. We have a transaction type. It has a user ID and amount, and then it has a list of transaction tags. And you just document and say, hey, there's always got to be one of these. Make sure you always provide one. And you can validate that in a couple of different ways. You can just put it at the point of consumption, just put a check right there and say, hey, look, you didn't read the docs, so if you're going to call this code, it's going to break. Or you can leave it up to another library to do and annotate it, get whatever thing you need to have process this. In the back end, it's just Java X validation. So whatever thing consumes that, and you annotate it at valid, it'll throw basically the same runtime exception. You can put custom messages, whatever you need. But again, it's a runtime exception. So as soon as you get someone who didn't read your documentation or who doesn't understand the fundamental root of what you're trying to do, you end up with a runtime error, and there's really nothing you can do about it at this point besides throw a runtime error. So let's look at how we might approach this. So I want to talk a bit about something called dependent types. Kotlin does not have dependent types, but dependent types allow you to validate qualities that people commonly think of as runtime checks at compile time. So you can constrain values. You can say, A is going to be less than B. Please validate this for me, compiler. And the compiler will do its damnedest. So I have something here that is what that might look like in Kotlin. It is not real Kotlin. Don't write this. It will not work. But you can imagine in 5 years, we have something called a sized list, and you can read that size out in your type definition as n and constrain it. That n must be greater than 0. Then, when you're compiling, Kotlin can say, hey, right here, it's a dynamically generated list. We can't be certain that there's an element. Or, hey, right here, you're passing an empty list. That has size 0. This isn't going to work. So this is a very narrow demonstration of what dependent types can do. But Kotlin has some limitations, and we're going to get some inspiration from outside of Kotlin here and say, I want this. How do I get it? In this very narrow case, if you're certain the list is going to have one element or more, you can just sort of pop off that head into a variable. Your type now is constrained exactly as you need it, so that you will always have at least one tag or more. So the way the validation code looks like this, the at valid annotation or anything like that, it looks like nothing. Your compiler has already validated it. If you get to this method, that thing is already true. So once you make your library change from the previous way you had it, the consumer is going to try to get around that, give you no tags, and they will not be able to compile their code. So that's sort of what you can do with dependent types as a thought. Let's say you got tasked with building a Kanban board. Your manager comes to you and says, we're really struggling to keep track of tickets. We really only like things we've built in-house, so we refuse to pay money for this, except to your salary. And you say, wow, you're insane, but I'll build it. So you go into a room and they say, you know, it doesn't make sense to be able to go from complete back to the to-do list. So let's constrain it. Let's make that impossible to do. So they come up with this diagram, this directed graph. You can go from to-do to in progress, to testing, back to in progress, along any of those arrows. So what might an implementation of this look like? So we have here ticket state, which is an enum, because we want to constrain those values. And we have a ticket, which is a name and a state. We might have more on it. I'm not building an entire thing for you. The implementation of this, you might make an extension method that says move to in progress. This will validate, like, hey, the state isn't in to-do or testing, so it can't move. But maybe you think, hey, if they're saying move to in progress, why don't we just ask them to transition to a state? And so you build this. Each ticket state has a set of allowed transitions, and you just give one method that says transition, and it tries its best. If it can't transition, it yells at you. So here again, we have our runtime errors as we expect, but we're going to try to push all of these runtime errors off to the compiler. So let's start from scratch here. We have a data class called ticket. It is parameterized by type T of ticket state. Ticket state is not the enum that we just saw. It is instead an interface. And we have objects, much like the unit object, which is just an object and a type. It is one thing. These to-do just exists. These are called phantom types. They don't do anything. You're never going to be passing around a to-do. You will only be parameterizing the ticket by to-do, or other stuff if you want, but all they do is exist. The reason all they do is exist is so that we can constrain things on them. We can make things true according to the compiler. So we might want to write something like this. Any ticket that's in state to do, you can give a move to in progress method. Similarly, testing. Now, I would bet that those implementations for this sort of simple drag and drop move around thing are going to look damn near identical. So let's see how we might be able to put a little extra varnish of abstraction on that and make some new interfaces. So we have 4 interfaces here, and they describe a trait on an object. This object is movable to do. This one is movable to done. And when we do this, we go back to our previous ticket state objects and say, let's implement those in terms of how they're movable. So the object to do implements movable to in progress, which implements ticket state, so it qualifies for the constraint that was previously applied. You can do this with all of them, and now we have codified exactly how everything is allowed to move within our system. You have to do can go to in progress can go to do or testing, etc. Done is a final state. There is no moving from done, so we have not provided a movable. You could make an immovable interface if you wanted to be very specific, but what this gets us is we can implement this. So any ticket that is constrained by or parameterized by something that is movable to in progress can be moved to in progress. And it returns a ticket that is in progress. And what that gets us in code is something like this. You can create a ticket, it's going to be in a to-do state. And from there you can move to in progress to testing. But let's say someone wants to try to cheat and they want to complete it right after in progress. Skip testing, they don't know what they're doing anyway. My code's perfect. Well, that's not going to work because the only thing that has the ability to complete is something that has the movable to done, which in progress does not. So from here, we can go and say, look, this is great and it works, but now we have this whole new concept, code review. People were leaving it in progress, some people were moving it to testing while it's still in code review. Everybody's muddled on this, so let's make a specific state for that. So your directed graph changes to this. Code review always comes between in progress and testing goes back to in progress. So you get this triangle in the middle here of movement. So we're just going to do a quick little live coding refactor. We have our original implementation, and we want to do some new fun stuff with code review. So we'll add this. Now we have a movable to code review. Anything we want to implement this can. And we're going to need a code review state. What do we know about code review state is that it can move to testing. And how do you get to code review? Well, you can move in progress to code review. So if you've done this, you're going to notice you get some compilation errors, which is exactly what you want. You can no longer go from move to in progress to move to testing. The fundamental lesson here is we don't want our business rules to break when we change code. We want our code to break when we change business rules. So we have changed our business rules and our code has stopped compiling. This tells us, look at these call sites, consider them, figure out what you did wrong, make them right. So this is obviously just some sort of test. So it's very easy to make right. Some other call sites might be really tricky and you have to think about it. But they don't just keep running and throw errors later. So last, I want to talk about something that is a bit more complicated. After your success with that cool new Kanban board, they want you to rewrite a checkout engine. And you know what your checkout engine code looks like, and you're pretty scared about it. But go into a meeting with some of your colleagues and management and talk about all the constraints around checkout and how checkout needs to flow. And you decide on some reduced scope for the new checkout, and you come out with this. This may look daunting. I'm going to walk through it real fast. Your starting state is you have no items. Then you can select an item, and then you have items. If you select another item, you still have items. You can begin checkout and add a card, verify the card, and place the order. From any of the steps after you start checkout to the point where you place an order, you can cancel that order. So you might start and think, all right, I can build all this code. I understand how all of this flows. So you make some class, some checkout object, and this thing has some items in it. It has a card, maybe, and it has qualities about it, whether checkout has begun, if the card is verified, and if it's complete. And from there you begin writing these transition methods. So you might write it like this. If checkout hasn't begun, you can add an item. That makes sense? That was in the rules. Otherwise, we're just not going to change state. We are the way we are. Your action is declined. Similarly here, we can select a card as long as checkout hasn't begun. That's actually not quite right. If the card has been selected, you can't select a card. And then if a card's been verified, that implies a card has been selected. Well, we're just going to... So you change that to really qualify what it is you can do, what state you're in when you select a card. This is implied state. You have implied that a card is selectable by these other properties rather than stating you are in a particular state. So you're going to do the same thing with verify and place order and cancel. It's going to look something like this. This is going to be, maybe it's not going to be buggy on the first try, but as it grows, you know this scope is going to expand. You know what your current checkout engine does, and you know that this doesn't do all of that. So what you're going to do, so you're going to keep refactoring it and changing it, add some methods that say, hey, is it in this current state? And every time something changes, you're going to have to go back in and change it. And you aren't always going to know what needs to change, especially as it grows. So what we really, really want here is to constrain the system so that when something changes, you can be plainly told, hey, this changed. Consider how you want this to act. So we're going to take that state machine diagram and we're going to treat it very literally. So we have some events that can happen here. A select item event contains an item. Beginning checkout doesn't contain anything. Selecting a card contains a card. All of the rest are just events that happen. And this is a sealed class, which is sort of Kotlin's way of getting algebraic data types. Now, how those work is essentially you can define a type that has multiple constrained states. Like in this case, checkout event can be a select item or begin checkout. And the compiler knows that. So in addition to this sealed class, you're going to get another one that represents all of the states a cart can be in. So this checkout machine has all of these different states. An empty cart is always the same, it's an empty cart. But everything else, it gradually builds up to this final state. And so if you want to handle all of the possibilities here, you essentially have to take the Cartesian product of all of these, which means for every pair, select item and no card, or verify card and cart with items, you have to decide how is this thing going to behave. And so the way we're going to encode that is we're going to handle an event, and that event is going to say, for each of these, let's shell it out to a method that we've written for that particular event. So if you get an event and it is select item, you handle it by selecting that item. So we're going to take a look at how select item is implemented in this first run through. You can see here that each of these things are handled appropriately and that we're exhaustive. You are welcome to do an else block in the when statement so you could handle the first two and do an else block for the rest. I find that in situations like this will lead you to skip over or miss something later on. So I prefer to be exhaustive, list out every possible state. So when a new state is added, you are forced to consider it. We'll see that later. But you write this and it works, and then someone says, hey, they've already selected their card. Why can't they add more items without canceling their order and starting over? And that gets run up and down the flagpole and comes back to you, and you go, all right, I'll refactor it. There, you've refactored it. You have taken this card selected and you have moved it to a card selected with that same card. So all of this code is totally in one line, and it's very clear. What are we doing? Selecting an item. What state are we in? The card selected state. So what's the output? Before, the output was no change. Now the output is change. If you contrast this with the way the add item method was written for the object, you'll see that we have this has checkout begun flag. Well, now checkout has begun, so this is wrong. Now you have to go back and consider what is the actual implicit state that you really wanted to achieve here. And I think it's that you have selected a card, but it has not been verified. But at any rate, the ability to check out is now codified through these other properties that essentially have nothing to do with that. And so we want to be as explicit as possible in these complicated scenarios. So that isn't the only change that comes down the pipeline. You end up with needing to apply a coupon after a card has been verified. So we have this new stuff in red. This is the flow we need to take and consider. So how much thought needs to go into this? Well, at this point, any new states and any new actions sort of start to almost write themselves. So we're going to write this new coupon applied state. It's going to have items, a card, and a coupon code because you've applied a coupon. And I'm going to skip over actually writing the apply coupon method. I think it's pretty clear what it does, but we're going to take a look at how place order begins to behave, because as we saw, the new coupon state is allowed to place an order. So here's our place order implementation after we have introduced this new state. You'll notice that it appears to be failing to compile because we were exhaustive the first time we wrote it, and we are no longer exhaustive. We have missed a state to consider. So to go about this, what are you allowed to do when you place an order? Well, it's pretty straightforward. It behaves exactly like what would happen if the card were confirmed. So now we've mapped this out. We have gotten our compilation error, and we have solved it. And we were told, hey, something is wrong with the way you have implemented this because the constraints have changed. And we couldn't build or deploy this without making or considering this change. And that's the ultimate goal, is that you can't make a change that results in a legal state. So, to sort of sum up here, if you are using the type system, you are already doing this. If you have ever made something non-nullable, you have constrained it very thoroughly. If you have ever done anything like I have described, if you've parameterized a list, you've already done this, right? The list can't just have anything in it. So, expressing truth in the type system offloads business logic to the compiler. This is essentially the point I made at the end of the Kanban board, you had business rules that you recently introduced, and they have stopped your code from ever building ever again until you fix them. You have to think about your business rules in order to implement your code. You don't have to implement your code while thinking about business rules. So the other thing is that thoughtfulness is key. This isn't just going to flow from your fingertips. You have to think, you have to design, you have to imagine what possible constraints you can apply to this. And importantly, with all of this, we want to explore different type systems. Knowing about ADTs and how they work help me out with thinking about how these things are. Knowing about dependent types, the phantom types on the Kanban board, all of them helped and produced better code because Kotlin supports these things to some degree if you force it to. And the only way to learn about those things is to go learn about it. Anybody have any questions? Or applause, that's fine.